Hello friends, today we are going to see self-inductance and mutual inductance. Now let us see self-induced EMF. Observe this figure carefully. Here there is one coil and in series with that coil there is one battery E, variable resistance R and switch S. Initially this switch is open. When we close this switch, circuit get complete and current I flowing through the coil. Now let this current be I. Due to current in the coil, there is a flux links with that coil. Let that flux be say phi. Now if we change the value of this variable resistance R, current will going to change. So as current changes, flux linked with the coil also get changed. And so according to Faraday's law of electromagnetic induction, an EMF is induced in the coil. Such EMF is called as self-induced EMF. Let N be the number of turns of this coil. So flux linkages for this coil equal to N into phi. The EMF induced in the coil due to change of its own flux linked with it is called self-induced EMF. Now let us see what is self-inductance. Now according to Lenz's law, the direction of self-induced EMF is so as to oppose the cause producing it. So this self-induced EMF opposes the change in the current through the coil. This property of the coil which opposes any change in the current passing through it is called self-induced inductance or inductance. From the Faraday's law of electromagnetic induction, self-induced EMF E equal to minus N d phi by dt. Now here it shows negative sign because this EMF opposes change in the current. Let flux phi equal to flux by current into current. Therefore, the rate of change of flux equal to phi by I into rate of change of current. Why this is so? Because this phi by I is constant and therefore when we take derivative of both sides with respect to time, then we get d phi by dt, that is rate of change of flux. It is equal to constant phi by I into rate of change of current, that is di by dt. But if we put this d phi by dt value in previous EMF equation, we get self-induced EMF E equal to minus N phi by I into di by dt. So it is equal to minus N phi by I di by dt. The constant N phi by I is called coefficient of self-inductance and it is denoted by capital L. So this self-inductance, it is equal to N phi by I, where N phi is nothing but flux linkages with the coil divided by I is nothing but current flowing through that coil, and unit of this self-inductance is Henry. Therefore self-induced EMF, it is equal to minus L di by dt holds. So from this discussion we can easily define self-inductance in several ways. The self-inductance is the property of the coil by which an EMF is induced in the coil when the current in it changes with respect to time. The self-inductance can be defined as the rate of change of flux with respect to the current in the same coil. So L, it is equal to N phi by I Henry, but we know flux phi, it is the ratio of MMF to reluctance, so it is equal to Ni by capital S. So if we put this value of flux in self inductance equation, then we get L equal to N into I divided by I into S. So it is equal to N square by S Henry. But we know reluctance equation, S, it is equal to small l divided by mu into A, where L is the length of the core, mu is absolute permeability, and A is the cross section of the core. Therefore L equal to N square upon L divided by mu A, and therefore finally we get self inductance capital L equal to N square mu A upon L, which is equal to N square mu 0 upon mu R into A divided by L Henrys. So let us see what are different factors affecting self inductance of a coil. L, we know this equation, self inductance, it is equal to number of turns square into permeability of free space into relative permeability into cross sectional area divided by length L. Self inductance is directly proportional to square of number of turns of a coil. This means for same length, if the number of turns are more, then self inductance of the coil will be more. Self inductance is directly proportional to cross sectional area of magnetic circuit. So if cross sectional area go on increasing, then self inductance also increases. Self inductance is inversely proportional to length of magnetic circuit. So if length of magnetic circuit increases, then self inductance go on decreasing. Self inductance is directly proportional to relative permeability mu R of the core. So for iron and other magnetic materials, inductance is high as their relative permeabilities are high. For air cored or non-magnetic cored magnetic circuits, self inductance coefficient is also small and always constant. Self inductance varies with respect to flux density. So these are different factors affecting self inductance of a coil. Let us see what is mutually induced EMF. Now observe this figure. There are two coils adjacent with each other. Now observe this coil A. One switch, one battery and one variable resistance is connected in series with coil A. And for coil B, there is a galvanometer to read the current flowing through coil B. Now when this switch is closed, current I1 flowing through coil A. It produces flux phi1 in coil A. The part of this phi1 flux is also associated with coil B. Let that part be phi2, and so this flux is called mutual flux. Let N1 be the number of turns of coil A. Let N2 be the number of turns of coil 2. Now if we change the value of resistance R, current I1 will going to change. So there is change in flux phi1. As this flux phi1 changes, some part of that flux phi1, which is nothing but mutual flux phi2, also get change. And so due to that change in flux phi2, there is a production of EMF in coil B. So from this we can easily define what is mutually induced EMF. So the flux produced by one coil is linked with another coil, and due to change in flux produced by one coil, there is induced EMF in another coil. Then such an EMF is called mutually induced EMF. That is, any change in current through one coil produces EMF in other coil. This phenomena is called mutual induction, and EMF is called mutually induced EMF. Let N1 be the number of turns of coil A, N2 equal to number of turns of coil B, I1 is the current flowing through coil A, Phi1 is the flux produced due to current I1, Phi2 be the flux linking with coil B. According to Faraday's law of electromagnetic induction, the induced EMF in coil B is E2 equal to minus N2 into d phi 2 by dt. Once again, this negative sign is there because this EMF opposes change in current, and therefore we can say that phi 2 equal to phi 2 by I1 into I1. If the permeability of surrounding is assumed constant, then phi 2 is proportional to I2. So this phi 2 by I2 becomes constant, and that's why we have now phi 2 equal to constant multiplied by I1. Therefore, if we take derivative of both sides with respect to time, then we get rate of change of phi 2 equal to constant, that is phi 2 by I1 into rate of change of current I1. Therefore, d phi 2 by dt equal to phi 2 by I1, that is constant, multiplied by di1 by dt. Therefore, if we put this d phi 2 by dt value in EMF equation of E2, then E2 equal to minus N2 into phi 2 by I1 into di1 by dt. It is equal to minus N2 phi 2 by I1 into di1 by dt. Now, this term present in the bracket N2 into phi 2, that is flux linkages with coil B, divided by current in coil A, is nothing but the coefficient of mutual inductance, that is capital M. So capital M, it is equal to N2 phi 2 flux linkages with coil B divided by current in coil A, Henries. Therefore, EMF E2, that is mutually induced EMF, equal to minus M di1 by dt holds. The coefficient of mutual inductance is defined as the property by which EMF get induced in one coil due to change in current through the other coil. It is also defined as flux linkages of the coil per ampere current in the other coil. M is also called as mutual inductance. Now, M equal to what? N2 phi 2 by I1, that is flux linkages with coil B divided by current in coil A, or M equal to what? Flux linkages with coil A divided by current in coil B. Phi 2 is the part of flux phi 1 produced due to current I1. Let K1 be the fraction of phi 1 which is linking with coil B. Therefore, phi 2, that is flux linked with coil B, it is equal to that fraction K1 multiplied by phi 1. Therefore, mutual inductance M, it is equal to N2 K1 phi 1 divided by I1. But we know flux phi 1, once again it is equal to mmf by reluctance equal to N1 I1 by S, and therefore mutual inductance M equal to N2 K1 by I1 into N1 I1 by S, and so M equal to K1 N1 N2 divided by reluctance S. If all the flux produced by coil A links with coil B, then fraction K1 equal to 1. Therefore, mutual inductance equal to product of number of turns of coil A and number of turns of coil B divided by reluctance, that is N1 into N2 divided by S. But we know basic formula of reluctance S, it is equal to length divided by absolute permeability into cross sectional area, so it is equal to L divided by mu A. Therefore, mutual inductance M equal to N1 N2 divided by L upon mu A. If we simplify this, we get capital M equal to N1 N2 mu A divided by L, which is equal to N1 N2 mu 0 mu R A divided by L. Now, phi 1 is the part of the flux phi 2 produced due to current I2. Let K2 be the fraction of phi 2 which is linking with coil A. Therefore, phi 1 equal to K2 phi 2, and therefore mutual inductance it is equal to N1 K2 phi 2 divided by I2, but phi 2 is N2 I2, that is mmf of coil B divided by reluctance. Therefore, M equal to N1 K2 by I2 into N2 I2 by S. So it is equal to K2 N1 N2 by S. If all the flux produced by coil B links with coil A, then K2 equal to 1. Therefore, M equal to N2 N1 divided by S. Now let us see what is coefficient of coupling or magnetic coupling coefficient capital K. We know now self inductance equal to N2 K1 phi 1 divided by I1, and M equal to N1 K2 phi 2 divided by I2. Now if we multiply these two M's, then M multiplied by M equal to N2 K1 phi 1 divided by I1 multiplied by N1 K2 phi 2 divided by I2. Therefore, M square equal to K1 K2 into N1 phi 1 by I1 into N2 phi 2 by I2. But what is N1 phi 1 by I1? It is self inductance of coil A. What is N2 phi 2 by I2? It is self inductance of coil B, and therefore M square or square of mutual inductance it is equal to K1 K2 L1 L2. Therefore M it is equal to under root K1 K2 into under root L1 L2, which is equal to K into under root L1 L2. Here K is nothing but coefficient of coupling or magnetic coupling coefficient, and it is equal to under root K1 K2. Therefore K equal to mutual inductance divided by under root L1 L2. So this coefficient of coupling can be defined as the ratio of the actual mutual inductance present between the two coils of the maximum possible value of the mutual inductance. Depending on the value of K, the coils are classified as tightly coupled coil and loosely coupled coil. When K equal to 1, then coil is called tightly coupled coil, and when K is less than 1, then it is called as loosely coupled coil. So that's all for today's session. Thank you.